My name is Mark Berkman, and in this webinar, I'm going to be talking about building thermal models of automotive batteries using Ansys Fluent and actually also TwinBuilder. So let's, talk about first what we're going to do today. I'm going to first introduce Ozen Engineering, which I'm a part of, and then go into overview of modeling strategy. And the heart of the presentation, it's going to be step-by-step model creation. And we're essentially going to see five the different tasks to build the model. And I'm going to talk in a lot of detail under each of these tasks. Well, Ozen Engineering, what do we do? We're a group of experts in simulations of structural thermal fluids and electromagnetic fields. And we also provide, Ansys support and licensing. We do training classes, mentorship, and consulting as well. We're actually, geographically are in two locations, the west coast of United States and also the southeast coast. And if you want to contact us, you may do by various means. Here you can see it, contacting different offices. Probably ozeninc.com is the easiest way. And we also, like I mentioned, do a lot of work with Ansys. We're a channel partner, so I thought it would be helpful to show some Ansys software tools. Use this slide from Ansys, which has a lot of strong engineering tools for structures, fluids, electronics, simulations, and not only that, optics and VR, photonics, design, semiconductors, and many more different engineering software is offered through Ansys. So now, let's start talking about a little bit about battery thermal modeling. This chart I took from the Ansys Learning Hub, and I'd suggest all of you to go there if you have an account. Shows, Ansys approach to do battery thermal modeling. So if we were to look at this chart, you can see different nodes, called like E1, T4. The top half is more so for electrical or a control engineer type work. The bottom half is for the thermal engineer, hence, T and E. As we go from left to right, we go from a smaller battery at a cell level, then we move on to a module level, and then at the most detail, it's the pack level. So it's at three different levels. What I've done is today we're going to work inside kind of this red box. We're going to be working on a module level. We're going to first work in TwinBuilder, start building our model, equivalent circuit model. Then we're going to move on to the thermal side of the problem, which essentially means using Ansys Fluent CFD tool as our thermal solver. Then we're going to build an LTI RAM, which is a reduced order model. So, CFD is not required anymore. Hook it up back to our TwinBuilder model, then this is going to become an, ET, more of an ETC tool. It will be like a systems tool. Okay. So what's the strategy? I touched upon it a little in the previous slide, but if we were to define it task by task, uh, we're going to do a lumped electrothermal modeling approach. So first step, what we're going to do is we're going to create an equivalent circuit model for our cell, for our battery cell. Then within TwinBuilder, we're going to move on to a module ECM. In the third step, we're going to first, talk about setting up the model in Fluent, setting up battery model in Fluent. We'll, excuse me, generate and then, execute the CFD model, make sure it works properly. Then we're going to generate a thermal step response in Fluent. Then, because CFD is costly, we don't want to keep running CFD in a systems type model. We're going to convert this response into a LTI ROM. And that essentially, it's going to generate really quick, thermal responses within our systems model within TwinBuilder. And once we couple the RAM and the ECM, we're going to have our full battery system model. And that is the goal. That's essentially the goal of this webinar is build that model. So, quickly talking about some concept, in order to build an ECM model, we need HPPS data. This is essentially a certain test, defined, and it provides us with information on battery discharge, uh, versus time involves, voltage profile during discharge. So this information we do need to define our cell model. Okay, so let's start with task one. Like we said, we're going to create a cell equivalent circuit model here. And we're going to do this using TwinBuilder. And to make it easy, there's a battery wizard defined in TwinBuilder for this purpose. And in a couple of steps, with the provided information, I'm going to walk us through on how to do it. So, the assumption is we have our HPPC test data, which essentially means for this particular case, 39 different curves in the correct format file. To be imported. So, going step by step. So here on out, I'm not going to use the software itself. I'm going to use screen captures from TwinBuilder or Fluent, and kind of show, which buttons to click and how to do the workflow, get to our final model. So we're going to open TwinBuilder, and then we're going to go to our battery wizard, which has two options, and we're going to use a cell configuration tool. That is going to pop up a screen like this. So, and once we do this page right, we're going to have our cell battery model available to us. So we're going to have 4 parameters. And we're gonna, put SOC and temperature options, and the way we're gonna do it is, like I said, using HPPC data. Then we're essentially in the step 6, pointing to that particular folder with the data, and we hit generate. So next step, in the component libraries window, which is to the left side of the TwinBuilder, we are going to see a new component, which we call battery cell, ready for use. Next step, now that we have defined our cell module, we're going to move on to our, move from cell module to cell to our module battery. So again, we go back to battery wizard. This time we're gonna move the module configuration tool. We're gonna select, and here we're gonna refer to our battery cell ECM that we have generated in the previous task, and our configuration for this particular example is 4S1P. So we want to decide do that, and we're going to use external loads. And these are the options for the output, and then we're going to say generate. And now, screen capture on the left side from TwinBuilder, what we see is now we have a new battery module. We see it and we take it and drag it into our canvas, and it is going to look like this in the canvas. So this one essentially this battery module has 4 temperature inputs and 4 power loss outputs. Uh, and that essentially concludes task 2. So what we do want to do is save our TwinBuilder model with an appropriate name. So we're now, up to task 3. So far, so good. The Fluent, portion or the workflow is the most involved, and the reason we're doing this is we're going to use Fluent as our energy equation solver and provide the cell temperature information from Fluent and couple it back to our ECM model. So it's essentially going to be a two-way coupling. That's the strategy. The cell heat source is going to be defined by the module ECM. Then, it's going to go to the energy equation, and the cell temperature will again, complete the feedback. So here, our goal is to generate a transient thermal response using Ansys Fluent. Okay, so how does this work? What we do is, we're going to open Ansys Fluent, open a standalone Fluent session, and read in the readily available mesh file. And I suppose I should maybe talk a little bit about more mesh file if, particularly you're not very familiar with CFD. So with computational fluid dynamics, what models, what you do is you discretize your domain, and it's almost like, FEA models where you have to physically represent your geometry with a mesh. So at this point, we have a mesh of our battery module where, details of the geometry of the fluids, if it's available, and the solids, all the detailed components, TIMs, tabs, the cells themselves, so that they should be modeled. And assumption is here that, you already have a good understanding of this and have built a valid mesh file that is available, that's appropriate for CFD use. So we open our mesh model. Then what we're going to do is go on to the left side view. Typically, the workflow is top down. So what we're going to do is turn the battery model on, because by default it is off. Then a new window is going to come up asking, requiring questions about the options. And here, we're not going to do any, circuit network modeling. So there's that. Keep that in mind. That's an availability within Fluent. You can also do some, circuit definitions and modeling in Fluent, which we're not going to do. That is going to be handled, by the TwinBuilder part. So all we actually do care about is, do an turn a battery model in and use conjugate heat transfer model. So CHT stands for conjugate heat transfer. That's the option we're going to select. And we're also going to have Fluent solve for Joule heating. So we set our model options. Next step is, the second tab, we're going to go to the conductive zones, and we're going to mark our 4 cells. Remember, we have, for SD1 configuration. And then we're going to tag the passive components where we have joule heating, and then define our electric contacts. Note that the whole model should be cleanly contacted through the mesh, and this is a typical error we get. If you don't have the connections made properly in the mesh, there's a chance you may get an error here. But obviously, in the particular model we're working on, all these issues have been resolved. So we mark our negative and positive terminals, and then move on to the fourth tab, which is the model parameters. And we're just going to say, hey, our batteries are 5 watts per battery. And then we define our current, and then we're going to hit OK. So that essentially will close the battery model. It kind of did the basic setup for the battery model. Then comes in the more so Fluent related setup. So in order to run a CFD model, of course, you need to define materials, right? So we go under solid, like I said before, we move top down. For the materials, we don't have any fluids for this problem. And we're going to start creating solids. And, actually, we're going to start defining solids. I'm sorry, because the solids themselves are actually already created in the mesh. So, we have this list of solids. So what we do is we click on each of those, and then we're going to assign them the correct material name. And then, we're going to assign the material properties to those materials. Another critical one is we want to make sure we have user-defined scalars to solve the joule heating equation for passive zones. So we're going to use something called a UDS, or a user-defined scalar. And that is, once we solve, we're not only going to solve the energy equation, but we're also going to use the user-defined scalar so that we account for joule. Let's see. All right. So once all the materials are defined and assigned, back to cell zones, another key aspect of CFD simulation is setting up boundary conditions. And here, I'm just going to show the only one example. If you have, and most likely, there are other boundary conditions at the wall. They could be adiabatic, or they could be fixed temperature. The important one in this particular case is we do have a cold plate on one side. So, and that wall is named wall HTC. And here, there's a strong convection cooling due to the water cooling, and then it's at room temperature, and it has a high heat transfer coefficient to cool the system down. And then we define our boundary condition like this. So, all right, this essentially finishes up the setup. We defined our material properties, the battery model, boundary conditions. Now, what we do want to do is initialize the solution, and that's the procedure in CFD. You do start with the initial solution. You do iterations to get the flow and thermal field to converge. So this is our first step to start solution. Then what we do want to do is we want to say, okay, how do we define convergence? I mentioned convergence, and this is, we define our criteria. So we want, an absolute 9 orders of magnitude reduction in energy and the scalar solution. So we define our convergence criteria. Next step is running this steady state analysis. And here, when we run that in Fluent, and for this particular case, this is not a very large model. It did converge within 15, 20 minutes. Uh, and as the model runs, Fluent is going to show you the residuals that we define versus iterations. And as you can see, we're nicely converging over 9 orders of magnitude. Then automatically the solver is going to stop, and we can check our results. And I'm not sharing any particular results here, but we essentially have a steady state thermal result at this point. So this is kind of the midway of task 3. We now have built our module battery model inside Fluent. And next step is to generate the reduced order model from Fluent to be used in TwinBuilder. So for this step, we go back to our battery model, and we start setting the model parameters to 0, because these are all going to be controlled by the process. And then we go to advanced options, the last tab. And then here you have, 2 buttons to make life easy. And the one, we're going to do is battery Ram Toolkit. So this wizard is going to guide us on how to build our thermal response in Fluent. So, we go to the RAM data creator for reduced order model. We're going to pick the LTI option. And then what we're going to do is select the cells. And, our input is the volume heat. We said heat is coming into the Fluent, and then it's going to put out temperature. So this is our input. We define our input, and then we also define our transient setup as shown on the left side with the time, and it's going to automatically do the time step size for us. And then let's see. Okay. In the next slide, then we're essentially once we define it, we're gonna click on make sure we have our transient set up right. We're gonna click run training. So this is going to take a bit more time to execute, and it's going to do the run for the time asked. And it's going to generate, you can track the progress on Fluent, essentially, volume average temperature in time, and then it's going to look like this. But the important thing it's going to do is it's going to generate 4 new files and create a folder called LTI. And you should be seeing these four files, and these are going to be passed on to TwinBuilder, where it's going to have the joule heat out and the volume heat out files. And now we can save the case and results file, and then quit Fluent. So step number 4. Now that we have our LTI RAM information, we want to process it into TwinBuilder. We go back to TwinBuilder. Again, go back to our toolkit, and then in step 3, we're going to say thermal model identification. So here, the window comes up. We have 2 inputs, 4 outputs for it. And then, we fill in these responses and mark to those the 4 files that we have generated, that particular folder, and then we hit generate. So here, now what happens is this is going to add a new item under the project components. So this is a new TwinBuilder model. It's going to have the thermal RAM in it. So what we have is we have our 2 inputs, volumetric heat, and joule heat, and then actually in this case an additional fifth temperature as well, just as a check. All right. So moving on. Now we want to test this system, so that we're going to start defining a time versus voltage definition. So we tie a data pair to the input as shown here. In the step 6, we're going to tie a joule heat source as a function of time as shown here. Then essentially, we want to read the data itself. So for that, again, what we do is, we prepare a lookup table and then essentially refer to it. So we have 2 of those, and then these are the steps to point to those particular files. And again, here the assumption is you have the data set in XY format, which is available, which has time versus voltage or joule heat information. All right. Then once we finish up the hookup, what we do want to do is we want to define an output. So we go, we mark the 4 outputs because we defined our inputs in the previous couple of steps. Now we say, okay, hey, these, we're going to select these 4 as the outputs, and let's take a look at them after the model runs. So we define some rectangular plots to see these 4 temperature outputs and define a new report. And the next step is that completes the setup. So now we want to do our transient analysis. We essentially have provided a time versus load in a sense for 1800 seconds, and now we're going to let solver solve for these time steps using the reduced order model. And this run will be immediate. As soon as you click analyze, immediately you are going to get the solution because this is a reduced order model. And what happens is, based on the input, you have time from 0 to 1800, which is our max. This is the thermal response, and the thermal response is as expected. So this task force says, okay, hey, good job. You were able to do the RAM, and we tested it, and it does work. So now we are sure that our RAM works. What we want to do is open the model again, open our model created at the end of task 2. So, we're going to go back to our equivalent circuit model and, add these details to build them further and to connect to our RAM model. We do these steps, and now what we do is we also, take these power loss from ECM, and then we want to sum them up. So all this, big green area, that's all it's doing is adding up the power loss to a single value. So we make these connections in the canvas. And now what we do want to do is open in the same TwinBuilder session, open the TwinBuilder model created in task 4. And that's our LTI ROM model. And the goal here is essentially, to take the TwinBuilder model from task 2, essentially our ECM model, copy it and place it into the same canvas or the same window as our RAM model. So now, the 2 systems are in a single window, which means they're in the same, model. And, essentially we're literally doing the coupling process. Here, we now, instead of data pairs, we are going to drive the model through coupling. So here, we're going to first do data pairs 2, which is the joule heating part. So we're going to give us source here, and the other input, the thermal input will come from the. So when we tie it, it will come from the ECM. So now, if we were to look at our RAM model, the two inputs are defined. So one is controlled by data pairs 2, and the other is controlled by the information that comes from ECM. And the temperature information out of the 4 cells, out of our RAM model, are tied back into the ECM model. So essentially, hooking these up using the steps 1, 2, and 3, we have now made the connections and coupled the two separate models. All right, so next step is actually, once it's all hooked up, we're going to hit the analyze button. And again, the run should be very fast because we're not doing any CFD. We're just marching through the 1800 seconds of time step. And then what we see is under the new load now. This is what our power loss looks like, and then we can save the finished model. And that actually does conclude my presentation. Thanks for your attention.